Ok, buenas tardes, sean todas y todos bienvenidos a la charla Drilling the Magma to Magma, que dictará en algunos momentos el doctor John Eichelberger, organizada por el Centro de Excelencia en Geotermia de los Andes, CEGA, de la Universidad de Chile. Esta charla será conducida y moderada por el doctor John Browning, quien es investigador asociado dentro de CEGA. Además es profesor del Grupo de Geociencias de la Pontificia Universidad Católica de Chile. También John es un geólogo de campo que utiliza técnicas experimentales de mecánica de roca con métodos de modelado numérico y analítico para resolver problemas en volcanotectónica y física de rocas. Actualmente es editor de la revista de diamante Acceso Abierto Volcánica. Sin más preámbulos, dejo con ustedes al Dr. Browning, quien hará además la presentación oficial del Dr. Eichelberger.
Muchas gracias, Pablo, y buenas tardes a todos. Hoy tenemos mucha suerte de recibir al Dr. John Eichelberger, profesor emérito de la Universidad de Alaska Fairbanks y un experto líder mundial en volcanología, geotermia y peligros naturales. Su carrera abarca 46 años, durante los cuales fue profesora en la Universidad de Fairbanks y trabajó con organizaciones gubernamentales y laboratorios nacionales. Ha sido fundamental para llevar al Observatorio Volcanes de Alaska y la distinción internacional. John obtuvo su licenciatura y maestría del MIT y su doctorado en geología de la Universidad de Stanford. Es realmente un investigador internacional que trabaja sobre todo en un proyecto para vincular los procesos de subduction en Japón y Kamchatka en Rusia y Alaska. Más recientemente ha estado trabajando en una iniciativa increíblemente emocionante en Islandia, de la que nos hablará hoy. John Eichelberger fue nombrado recientemente uno de los 2 conferencistas distinguidos de 2020 por la División de Perforación Científica Continental de la Sociedad Geológica de América. Nos sentimos honrados de que haya aceptado nuestra invitación para presentarnos hoy. So John, I was just giving a very brief introduction to your career. I could have talked for hours just on that because you're incredibly distinguished. And I was just saying, thank you so much for accepting our invitation. And we're very excited to hear about drilling to magma and the research you've done. So if you can share your screen now, John, and unmute yourself, and then it's over to you.
Myself.
Great.
Okay. You can hear me?
We can hear you fine. You might want to make, or at the moment we can see the drilling to magma sort of in the side and a picture in the middle. So I'm not sure if you want to make one of them.
I will. I will. I just wanted to say that I'm very pleased to be in Chile. This is Laguna del Maule. Fantastic place. I love it. I've been there twice. If you want to find a rhyolite magma chamber, I think that's probably one of the best places in the world to do it. So I'm honored to be here. I love Chile, wonderful people, great scientists, fantastic volcanoes and lakes and glaciers. How could it be better? I don't know. And as I was telling John Browning, my first visit was in September 1973, and things were a bit difficult then, but I'm glad to see that things are much better now. And I wish you good fortune and your upcoming election, and we will need good luck as well.
It's true.
Okay. Let's see. So now I will go to my talk. Here we go.
I'll just say as well, John, that if people want to make questions or comments, they can put their comments and questions in Facebook, directly on Facebook, and then I'll ask those questions to John after the presentation. Entonces, si quieres hacer un comentario o una pregunta, puedo hacer eso en los comentarios de Facebook y voy a preguntar a John después de la presentación. Okay, John, many thanks.
Thank you, John. Well, I want to talk about drilling to magma, which is a subject dear to my heart. I have been kind of obsessed with it since quite early in my career when I got involved in drilling into lava lakes in Hawaii. And it was so exciting to get core out of the molten part of the lava lake with basically olivine phenocrysts set in beautiful black glass. My hope was that I would eventually, later in my career, drill to magma. Well, for a long time, that looked like it wasn't going to happen, but then it happened by accident. And so now I am trying to develop an international effort to go back to the site of the accident and do some important science and perhaps geothermal development. So that's what I'm going to talk about, is drilling to magma. This view is looking, I can never remember which direction. I'm always turned around in there. Well, it doesn't matter. It's looking across Krafla Caldera. And in the foreground, you can see this is a tourist stop, but in the foreground is VT Crater, which is very much smaller than the caldera itself. It formed in 1724 in a phreatomagmatic eruption. And it's significant to our story because it brought up fragments of rhyolite magma, which were then intersected by drilling about 1 kilometer away. And VT means devil. So it's, and I think, let's see, Villa Rica in Chile has something to do with the devil, doesn't it? I don't know, anyway. And now a word from our sponsor. I was selected by the Geological Society of America to give a lecture series to promote the interest in continental scientific drilling. As you may know, there's an international continental scientific drilling program based in Potsdam, Germany, that is kind of the coordinator of this effort. And the idea is to promote the use of drilling on the continents as a research tool. Just like doing field work is a geological research tool, well, drilling gets you the third dimension. So this is an effort to get people interested and also tell my story, which I hope you will find interesting. I found a quote from a guy who I took chemical thermodynamics from ages ago, more than half a century ago, when he was awarded the Day Medal, one of the most prestigious medals of the Geological Society of America. And I've modified it a little bit for this case, but he said true success in the laboratory and in modeling should stimulate field and drilling investigations rather than discourage them. Would be embarrassing indeed if we were to construct an internally consistent geology, chemically and physically sound, perfect in fact for one flaw, the lack of a planet to fit it. And that's how I feel we're in that state with magma. We have models that are internally consistent, incorporate physics and chemistry, and yet we don't know what planet these models belong to. Nobody really knows the reality of magma in this planet, but many people think they do. Well, I'm going to center my talk on Krafla Caldera, which is at almost the same latitude where I'm sitting. I'm sitting at 65 degrees north, which is 100 degrees north of you. And Krafla Caldera is at about 66 north. It's a modest-sized caldera, about 10 kilometers in diameter. That's the yellow line. The red dashed line is the approximate extent of the rhyolite magma chamber that was discovered by accident and is only at 2 kilometers depth, which is, I think, just amazing. And you can see the caldera is cut through by lines. Those are actually rift structures that divide the North American plate from the Eurasian plate. And the spreading here is at about 2 centimeters per year. So basically, we're where the mid-Atlantic ridge is above sea level. So in 2009, another project, the Iceland Deep Drilling Project, in an effort to reach supercritical fluids, which have 3 times the energy content and are much more, and are 3 times as efficient when you put them into a power plant in generating electric power. So in principle, if you could access these high pressure, high temperature fluids that are beyond the boiling point curve in pressure and temperature, you could increase the productivity of geothermal energy by an order of magnitude. And geothermal energy is a wonderful thing in many ways. One is it has the smallest footprint of any power source because it doesn't need a separate mine or drill field, and it doesn't need a separate waste disposal site. And it's low or no carbon dioxide emission, but it accounts for less than 5% of electrical power production globally. So if it could be made much more economically beneficial, it could be an important part of the solution to climate change. Well, another very surprising thing. So I never expected, by mid-career, I thought, well, this isn't going to happen. We're never going to see magma quenched at depth. Why do we want to see it quenched at depth? Because a lot of bad things happen to magma on the way up to the surface. It boils, essentially, fasciculates, loses all its volatiles, and usually undergoes some crystallization because of the loss of water. So we're not seeing real magma. And, but here we are, another thing I never expected to see were X-ray, it was X-ray tomography of rocks. But here we have phenocrysts depicted as green fish, plagioclase, sodic plagioclase, and pyroxene swimming in high silica rhyolite melt. And this was quenched at 500 megapascals, half a kilobar, and 900 degrees Celsius. Well, this is not just a freak accident. It's happened more than once at Krafla Caldera. It happened earlier at the Puna geothermal venture on Kilauea volcano. And it happened multiple times in Menengai caldera in the East African Rift in Kenya. And all these occurrences, the depth of the magma is between 2,000 and 2,500 meters. I think shallower than any volcanologist would guess before this that magma would be quietly sitting. Well, we've been drawing cartoons about these kinds of systems, magma hydrothermal systems, for a long time. For a long time, we've recognized that for a hot hydrothermal system, you've got to have a magmatic heat source pretty close by. And the general concept has been, okay, you've got a hydrothermal system where there's convection of aqueous fluid by a porous flow, and that's being driven by heat from below. And the heat comes from comes through a conductive zone. Why is that? Well, because at high temperature, you're above the brittle ductile transition, so fractures can't stay open, so you can't have circulation of water, and therefore you only have conduction. And then below that, you've got magma. Now, and you can see this reflected in these kind of general temperature profiles. You have almost isothermal situation at pretty high temperature. 250 Celsius would be typical for a geothermal system. And because it's convecting, it's close to isothermal, or it may be limited by the boiling curve. And then below that, at some point, you have this conductive boundary where you don't have convection going on, you just have conduction. And so that's a much steeper thermal gradient. And then you go back into a convecting system, in this case, whole convection of magma. And again, now you have a less steep, because of convection, thermal gradient, because the heat is being transported by the motion of the liquid rather than the very slow process of conduction. You can think of this, if you want to think of it as in electrical terms. Here's a low value resistor, a high value resistor, and another low value resistor. So if you say, well, temperature is a proxy for, say voltage is a proxy for temperature, then you'll have a big temperature drop across the big resistor. Well, the important thing to realize is that we know a lot about this part of the system, the hydrothermal part of the system, because it's been drilled many times all over the world. We know virtually nothing about this part of the system, the magma, and very little about the boundary zone in between. And that boundary zone is incredibly important because what's the distance? Nobody has known. Lots of petrologists have guessed, but trust me, don't believe igneous petrologists when they tell you what the pressure of the magma is under. I mean, I am an igneous petrologist, but it's all what you can get past the reviewers. It has nothing to do with reality. And the reason why this is important is that It controls the heat flow out of the magma into the hydrothermal system. The shorter it is, the higher the heat flow. And it records the response time because suppose new magma comes into the magma chamber and gets hot. When is the hydrothermal system going to get hot in response to that? Or suppose you start sucking geothermal energy out of the hydrothermal system. When is the magma going to feel that chilling effect and hopefully start convecting faster? Well, as I said, we know an enormous amount about these hydrothermal reservoirs because they've been drilled for economic reasons, and there's nothing like money for motivating people to get things done. Just for example, going back to Krafla, within that caldera, there are about 40 boreholes, generally to about 2,000 meters depth. And all of them have been logged. There's been a little bit of coring. But so what do we know? We know this incredible detail about the temperature distribution within the system. The height of this image is a little more than 2,000 meters. And the width is about 2,500 meters. We know the lithology in detail from cuttings recovered during drilling and occasional coring. We know we have an idea of composition from gamma logs. We know porosity, permeability, and temperature, pressure of the fluid, composition of the fluid, practically everything anybody would want to know about this. And this goes into sophisticated models of what's going on in the system and how much energy you can pull out and so on and so forth. What nobody would have predicted, and you certainly wouldn't from the temperature field here, was just a little bit deeper, really only about 50 meters deeper, was high silica rhyolite magma, and not just, mushy stuff, but actually almost pure liquid. So almost at the liquidus. An absolutely remarkable result. Now, of course, I've indulged in fantasy again. We only know what's right there at the bottom of the drill hole. And so I've embellished things a little bit, but still, we actually have a data point on where this stuff is and what it is for the first time. Well, this was a big surprise to everybody, most of all the geophysicists, because they were after fluid, aqueous fluid, not magma, and they didn't want magma. There was a general idea that there was magma at, maybe a few kilometers depth, certainly not 2. And nobody wanted to hit that. So they went to some length to try to avoid it. And obviously they failed to avoid it. What's the problem with these guys and women? Fortunately, the portion of women is increasing at last in geophysics. Well, they've never had the benefit of testing their models against reality. If you do geophysical prospecting for oil and gas and you convince management that that's where it is, it'll get drilled and you're right or you're wrong. If you're right, you celebrate, oh, we're using the right methodology and so on. If you're wrong, you kind of slink away and think, oh, what did I do wrong? Well, I got to change this and that and the other thing. So with time, and testing, you get better and better at this. That's never happened in looking for magma. It's again, the only test is whether the reviewers of your manuscript agree with you or not. It has nothing to do with planet Earth. Now, of course, there has been a lot of progress in how much data can be incorporated, how much different parameters are incorporated in interpreting geophysical data. But again, the big thing is the lack of testing. So we have the situation where drilling saw, geophysics saw magma where it didn't exist. Long Valley Caldera, a super volcano on the eastern front of the Sierras. I'll talk a little bit more about this as being in the giant balloon phase of igneous petrology. But in the United States, there was a search for magma, and the consensus of geologists, volcanologists, and geophysicists of all kinds said, well, this is the best place in the United States to look for magma. And we found a temperature of 100 Celsius at a depth of 3 kilometers, which should have been about halfway to magma. One of the intriguing things was this caldera was inflating at the time, almost a meter over a decade. And that was attributed to influx of new magma. So instead of setting a high temperature record, we in fact set a low temperature record. Needless to say, that was, well, this was a pin that poked the giant balloon. Now, it's the opposite case at Krafla. People didn't want magma. They wanted fluid, and to get to supercritical conditions, although this is a long discussion, there's much debate about what to worry about here, or even if the term supercritical should be used at all when it comes to the real Earth. But I won't get into that unless you want to during the discussion. But they looked for places where they had located earthquakes that indicate that the rock is brittle, therefore no magma, and where it's conductive based on magnetotelluric studies. And so they picked a point which they thought was very good, and lo and behold, less than halfway to the target depth, they hit this almost pure melt near liquidus magma. Big surprise. It's not what they wanted. A little like landing on the moon and saying, oops, this is the wrong planet, we'll just go away. So that was the end of that. Well, now for the first time, geophysicists could go back and see where magma, if you know the answer, you can figure out the question. So they went back, and seismologists in particular were able to locate the magma now that they knew where it was as a VP-VS anomaly, low VP-VS ratio, and as a strong reflector. So bingo, now we have some geophysics that actually shows it. Now, what about magma chambers themselves? Well, these are purely intellectual exercises that throw out the textbook, that incorporate as many observations as possible. They've gotten more and more sophisticated with time, but again, they've never been tested. And now we've had 3 drilling encounters, and in every case, you go very abruptly from solid rock into mostly liquid magma. None of the models, in fact, or none of the recent models would say that, because you're losing the most heat through the top of the body. So you should have the most crystallization going on there. Instead, we've got this basically pure melt. And so these are, it's probably about 1 millimeter across here. From the 3 sites I mentioned, magma quenched at 50 to 70 megapascals, temperature of 900 Celsius, 0 to 10 volume percent crystals. Well, let's look a little about the history of magma mythology. I want to emphasize to students that I think the real discovery, many of the real discoveries are to be made where people already think they have the answer, but they can be completely wrong. Well, an example is how old is the Earth? Physicists said, well, you know, a sphere that size will cool off in about 500 million years, so it can't possibly be, and we know it's still warm inside because they're volcanoes, so it can't possibly be older than that. Well, there was something they didn't know about until Madame Curie came along, and that was radioactivity. That's a big deal. So, you know, you can be missing something and think, well, I got it nailed. Well, probably the earliest ideas were that these were mostly liquid bodies that chemically evolved because the crystals are of different density than the melt, and therefore you get, by gravity, you get separation of crystals and melt, and the bulk composition changes because of that during crystallization. And that certainly happens where melt is very fluid in basaltic systems. But in rhyolitic systems, the melt is very viscous and the crystals are very small and not so much different in density from the melt. So you got everything working against you, and basically hell freezes over, or more accurately, the magma chamber freezes over before the crystals can move very much. Well, volcanologists came along and recognized that there were vast volumes of melt-rich magma erupted in a short period of time, supervolcanoes. And that led them to postulate these giant melt balloons and to look at some kind of differentiation process that involved mostly silicate melt rather than crystal settling. And this started out with the bizarre idea of soiree effect, basically because at Long Valley, nothing else seemed to work. Wes Hildreth published a great deal on this kind of thing. In fact, he's worked in Chile quite a bit. He does very careful field work. I would say kind of wild ideas as far as magma goes. But anyway, soiree didn't work, but eventually this evolved into some kind of fancy double diffusive convection where you have a thin chemical boundary zone producing silicic magma that collects at the top of the magma chamber, while a broader thermal boundary zone drives normal convection. And along with this came the idea that a supervolcanic eruption only involved about the top 10% of the magma body. Well, so geophysicists couldn't find these giant melt balloons. And people became discouraged, especially after this drilling experiment at Long Valley, and shifted dramatically from thinking about giant accumulations of melt to giant accumulations of mush. That is near solidus magma with a little bit of melt between crystals, and you could have some kind of catastrophic event, maybe a tectonic one, that would cause sudden expulsion of melt from this mush, like squeezing a kitchen sponge. And you then have, for a short term, you have a large body of melt that then erupts entirely. This gets the geophysicists off the hook because they can say, well, there was a big body there, but you can't see it now because it all erupted, and we have to wait a long time, about a million years for the next one. So give me a break. Well, so much has been published on these themes. Simple mush, Bachmann and Brigance, very complicated systems of smallish magma bodies and a lot of mush, Cashman and Sparks and Blundy. And then very recently, a sophisticated kind of classical egg model, but you'll notice a great deal of mush at the outer portion of the magma chamber and nothing much going on in the middle. So mush is all the rage these days. But strangely, we didn't see any mush. And in fact, in none of these encounters with magma has there been mush. In fact, at Krafla, there is roof rock caught in the process of partially melting. Now that's mushy in the sense of mostly crystals, but it's quite a different process from what people call mush, and I'll talk about that a little bit. Well, I already showed you the theoretical temperature profile in a coupled hydrothermal magma system. And for the first time now, we've got a constraint of the temperature drop across this conductor. So that gives us a temperature gradient, 16 degrees centigrade per meter, which includes, if you know the conductivity of felsite microgranite, and we do, that gives you a heat flux of 24 watts per meter. And that's the first indication ever of the heat flux from a magma body into a hydrothermal system. And so basically the old cartoons are right. And it looks like here we've got a step function in temperature with depth. We don't, we just have an extremely steep thermal gradient across the conductor. And then right at the bottom, what do we have? This strange juxtaposition of partially melting roof rock and almost uncrystallized magma. So the old guys were right, and they were guys back then. Except that the separation between the hydrothermal system and the magma was not 2.5 kilometers, it was 25 meters. So even in astronomy, that's where you want to be within an order of magnitude. It's not that good. I want to clarify some terminology because petrologists and geophysicists tend to talk different languages. It's getting better. What really is a different language is geothermal engineers and scientists and volcanologists. And that's the connection we really need to work on because we're each only looking at half the elephant. I'm not sure which group is working in the hind end and which has the head. Anyway, so magma is not just any rock containing melt, it's one capable of flow and eruption, usually considered to be more than 50% volume percent because less than that, the crystals get in the way and it can't flow. geophysicists would say partial melt. And that's a bit of scientific caution. They don't want to say exactly what the melt fraction is. Well, they'll estimate it from like seismic attenuation or something like that. But they're being cautious about it. Then in petrology, we have partial melt, and that's melt in the process of forming within a rock, but it's still a rock. It's not, the melt is not in sufficient proportion to actually flow, satisfy the magma definition. And to get a magma, you've got to either melt it more or you got to squeeze out the melt. Again, geophysicists would use this as a general term for where they see a seismic anomaly that looks like requires melt to be present. And then mush, for those of us in petrology, if I may speak that broadly, it's crystals plus melt formed by either crystallization of a magma or accumulation of crystals, accumulate with less than 50 volume percent melt. So again, it doesn't satisfy the magma definition of being able to flow. Geophysicists seldom use that, although now geophysicists, in hanging out with volcanologists in bars, have picked up the lingo of mush. Okay, you can ask, how is it possible to drill magma? You can't drill a liquid. This is a brittle process of grinding rock. You can't grind liquid. Well, what you do, so you can't drill water, but you can drill ice. You can go ice fishing and drill ice and pull fish out the hole. Well, what we're doing here is actually turning the magma to glass just ahead of the drill bit. So then it's brittle, so then we can drill it. And we're quenching it, so we preserve basically all the chemical properties of the magma. And even so, but it doesn't flow. It's a liquid that doesn't know it's a solid. That's what quenching is all about. Now, the most common kind of drilling uses a Trichome Bit, and that's usually done in oil and gas fields and geothermal. It's the most cost-effective way to make a hole, and you put water down. Usually, you can do reverse circulation, but you put water down the drill stem that comes up the annulus with chips. And these are very small, so you lose the things petrologists love, like texture, veins, that kind of thing. But you do see what's down there, basically. And you also don't know exactly where things are coming from. Presumably, it's mostly coming from where you're doing the cutting, but really it can come from anywhere up the hole below the casing. Coring is a much more wonderful thing because you're getting out large intact samples of rock, and you do that with a annular bit, and so you're cutting a donut and the core rides up inside. If you're doing what's done in hard rock mineral exploration, wireline coring, you can actually send a cable down and yank this thing up, and it's wonderful. But that's what we did in Lava Lakes. It's cool. And when you get into molten rock, you're actually making a glass casing around the borehole. Notice that you've got to select the right penetration rate if you're very slow, you're not going to get good quenching. It's going to be slow cooling. And God forbid, if you go too fast, you're going to outrun this quenching front and end up in the soup, and you will be stuck. Well, so we learned a lot. Before these accidental drilling into magma bodies, people did a lot of drilling into lava lakes, and that was the best proxy we had for what a magma chamber is like. And these were drilled repeatedly over time, and they recovered a lot of information about cooling and crystallization behavior. And also you can see the lovely core. These are olivine crystals, and they're olivine crystals here, but with more melt. So you can see there's a nice gradient there. You can get all kinds of information out of that. One is a liquid line of descent by actually getting this melt and being able to measure the temperature where you got it. This would be, that's a basaltic melt up here, high in calcium and magnesium, and close to the composite, a large portion of melt in the rock, and near the bulk composition of the basalt. As you cool down, you get less and less liquid. You crystallize various minerals that are lower in silica content and calcium and magnesium and so on. And then you end up with a little bit of rhyolite melt in a rock that's still the same in bulk composition, basalt. That's quite a high temperature, but remember that rhyolitic melt is anhydrous. It's degassed on the way to the surface. So that's one big difference between a magma chamber. Now, this tracks, it shows that lovely conductive zone, and the hydrothermal system is actually chasing the melt present zone down toward the center of the lava lake. That's because there's thermal fracturing going on as the stuff cools, and crystallization going on in the front. So this conduction zone is advancing by crystallization at the front and thermal fracturing by contraction at the back. That's how you get columnar joining. You've all seen that. Well, this means we can get the heat flux from the melt zone, and we can make the hypothesis, okay, the heat released by crystallization of the magma, say over a year between drilling, has got to equal the heat being conducted through that conductive zone. We've got two ways of inferring the amount of heat involved, and they ought to agree. So we look at the temperature gradient, we multiply by the conductivity, and we get a heat flow of 130 watts per square meter. And by the way, you integrate that over the area of the lava lake, you got about 20 megawatts thermal output. That's a couple decades after the thing was filled. Because rocks are lousy conductors, that's why. They're insulators. You can build a house out of rock. People do it. Now we can also calculate the flow, the heat that's being generated based on the advance of the solidus per time times the, and that should be a rho, not an R, energy density, which includes two things. One is just you get sensible heat out, not nonsensical heat, but by cooling, heat comes out, but also by crystallization. And that's the big term. Just like water, freezing water, the big term is not going from 0 Celsius to 0 Celsius. It's going from water to ice. And we play that game because we know how fast the crust is growing, and we get 126 watts per square meter. That, I confess, is better than we deserve, but we'll take it. So either we predict from the temperature gradient in the conductive zone crustal growth of 2.4 meters per year, and we observe 2.3 meters per year. That's pretty good. Now, if we try the same thing at Krafla, because remember, we've got a minimum constraint on the temperature gradient in that conductor that bounds the magma from the hydrothermal system, we get 24 watts per square meter. That should give us almost a meter of growth at the crystal growth at the top of the chamber per year, but in fact, there's none. We're seeing the reverse. We're actually seeing melting of the ceiling of the magma chamber. Now, some people tried to squirm out of this by saying, well, the magma body just came in before we drilled it. Well, give me a break. I mean, that's cheating and special pleading. For one thing, that caldera has been geodetically instrumented for 30 years before this magma was hit. And by the way, that lovely place behind me is inflating at 20 centimeters per year, which is pretty amazing. But you can't sneak in even a tiny sill when you've got a GPS station or SAR interferometry right above you. And if you did sneak in a tiny sill, it would freeze right away. So it's not possible. It had to be there at least before the volcano was instrumented. And during that time, there should have been about 20 meters of crystallization at the roof if it were like a lava lake. And in fact, VT crater next door erupted exactly the same stuff almost 300 years ago. So it's been around for a while. Now, strangely, no rhyolite has been erupted from Krafla in the last 10,000 years, which is another lesson. Contrary to what volcanologists would like to believe, eruptions don't really tell you everything that's down there. There can be a sleeping giant 2,000 meters below your feet that hasn't peeked out, except for that little crater, for millennia. So this is another view. We don't actually know. The Icelanders are kind of amazing. They do what I was told to never drill, drill blind, that is without cuttings coming back. You have to get cuttings out to have a hole, just like if you went out in your backyard and dug a hole but didn't take the dirt out as you dug, you wouldn't get anywhere. So it's not best practice. But they just blasted ahead. Presumably the cuttings got stuck into cracks, and then they actually got stuck in magma. They found they were drilling in hard rock. Suddenly they drilled into what they called a soft formation, and they noticed that the weight of the drill string, which is measured all the time, it had lost 50 metric tons of weight. Why? Because the magma down here is under lithostatic pressure. The borehole is under hydrostatic pressure, column of water. That's a big difference. It's about 30 megapascals, and that was pushing up against the drill bit. So they pulled back. They pulled back 8 meters, thinking all was well, and the thing came up and chased them, and they got stuck. Well, that's when, for a brief period of time, circulation was restored for whatever reason, and these chips of partially melted magma roof and quenched magma were recovered, but no mush. Well, why does our heat hypothesis work for a lava lake and not for a magma body? Well, I think the most obvious answer is there is no convection in a magma body. There is very early, but basically you've got a system that's small and it's losing heat from both the top and the bottom. So it stops convecting pretty soon. It just is crystallizing in place, where the only way to explain, I think, there has to be heat loss and crystallization going on at the roof of this rhyolite magma body. But I suggest that it's not, the crystals aren't sticking to the ceiling. Instead, they are staying within the magmatic flow and actually increasing the bulk density of the downgoing limb of the convective cell. Also, in order to melt that felsight, you have to add water. Remember the anhydrous case, you'd have to get up to way above the temperature of this rhyolite magma that has 2% water in it to melt the roof. So you've got to add water, and that will reduce the density of the magma as well. Well, to wind up, let's think about this. A conventional hydrothermal reservoir and a magma reservoir is a thermal battery. How big a battery do you need? Like, how big a battery do you need to drive your car from Santiago to, well, not Chaiten, you'd have to take a ferry in there, but, oh, come on. Valparaiso. Or Concepcion or something. How big a battery do you need? Well, you can figure out how much energy you need, and well, how much power you need and over what period of time. So that's energy. So in the case of geothermal, we'll take 30 years, and because that's a kind of business horizon. And we're going to cool the thing. We're going to extract energy by cooling the reservoir 100 degrees. In the case of magma, we'll be cooling it from the liquidus to the solidus. This is just a thought experiment. We're not going to get all the energy out of this thing. You can see that the volume you need for a conventional hydrothermal system to extract the heat from is more than 5 times what you need for your magma battery. And the big difference is here, and notice that even with the supercritical fluid, that doesn't add much energy to the system. It adds to how fast you can transport the heat, but not to the system, because that's a low density fluid occupying porosity in the rock. So the weight fraction that's supercritical fluid is small. Not so with the magma body, and the big term there is latent heat of crystallization. And not only that, whereas this material, your hydrothermal reservoir, is static rock, and rock is a lousy way to store heat, as I've said. The magma will convect. So in a perfect world, you start taking heat out of it, it will bring more hot magma toward you. It will convect. What does this mean? Well, we have a long way to go to truly understand magma, but we can have a glimpse if we go there with scientific intent, not just stumble in it by accident, we can learn a great deal. For example, we can get core, we can measure a temperature profile up to the magma, etc. The group I'm involved in believes we must go back to that magma at Krafla, core of the rock magma transition, measure equilibrium temperature profiles, and eventually experiment with extracting magma and instrumenting magma to forecast eruptions. Don't forget, and I'm sure you haven't forgotten, that magma can do bad things to you if you erupt. If it erupts, and presumably this involves an increase in pressure in the chamber and probably an increase in temperature too, because these eruptions involve new magma coming in. And people are now spending billions literally on developing extreme sensors. So there's a real possibility of instrumenting magma bodies directly. So that's the vision, is an international observatory and laboratory, like a particle accelerator, which, for example, your team could come to and do measurements or experiments, both potentially on the surface and in the borehole, and with multiple boreholes. And the potential benefit to geothermal energy is huge. If we can get the liquid that comes right adjacent to the magma body and is sustainably heated by convection of the magma body, we can see an order of magnitude increase in productivity, energy productivity. Well, I suggest the take-homes here are magma hydrothermal regimes need to be treated as a single system of heat and mass transport. You have to look at them together. And geothermal engineers and magma scientists really need to be talking to each other. And we need to persuade the geothermal engineers that magma is not just a thing for pointy-headed academics to think about. It's their mother lode, it's their source. They just need to drill a little bit deeper. Well, thank you very much for your attention, and I'm happy to answer any questions you might have.
John, many thanks. That's incredibly interesting. Many thanks for the presentation. So on Facebook, we have several people who have made comments, and so there are some questions that were asked out, and John has offered to have a discussion with us, so he's happy to do that. So if you have more questions or comments, please put them on to Facebook or YouTube now, and we can ask John. So the first questions or comments come from our colleagues in Peru, the Peruvian Geothermal Association, and Francisco Putoras, and he asks several questions. The first of which is, what do you think, John, are the best methods to obtain semi-quantitative data to evaluate heat flow anomalies in terms of geothermal systems?
Well, drilling.
Yeah.
That's the only real truth. But I guess before you do that, a combination of seismic and magnetotellurics, I guess, are the.
I guess for a country like Chile or Peru, perhaps, where maybe our funding is somewhat more limited, I'll come back to Francisco's other questions, but the question I had was how much does drilling cost, essentially, because presumably this is mega expensive, right? So would this be I guess one of the last options to go for if you have a lot of data first, or how do you reconcile that potential cost?
I think if if the initial drilling is what they call slim hole, the kind they do in hard rock mining, coring, then the cost can be relatively modest. You might, if you're lucky with a truck mounted rig, you might get to 1,000 meters or so for I hate to give a number, for maybe $1 million. It's not a huge amount more than a detailed seismic survey or something like that. Those are very expensive as well. And then you'd actually get a complete, continuous core, complete lithology, permeability values, and most of all, temperature, real temperature. And even with a big borehole, I would think that doing that sort of thing first would be worthwhile. There are other things that you get out of it, where to have casing points and so on from stratigraphy. Now a serious geothermal well, where you're going to encounter, where you're going to have to be prepared for high temperature, and you need to be prepared for high temperature whether you get it or not, then we're talking about an order of magnitude in cost, $10 or $20 million. I think the Krafla hole cost that, but if you've managed to prove the resource with a reasonably high probability, and I'm not really an expert in this kind of development, but if you've proved the resource, then you can get the money, because there's money to be made. I am really intrigued by Laguna del Maule. There's a tremendous amount of geophysical data there now, and petrologic data, a lot of it from scientific imperialists from the United States. But the data is there. Who cares where it came from? And it's completely open. Now, that's right next to Enel's huge development, hydropower development, where they're putting all the rivers underground and running them through turbines and so on. It's easy access. You could drive a truck-mounted core rig up there, maybe barge it across to the center of inflation and core down 1,000 meters. And you'd learn as much as the NSF project did, probably with less money. I mean, and then, if it proves out, surely Enel would, I don't like to talk about other people's countries and what's possible or not. Just consider that I'm talking off the, as we say, top of my head. Then you've got Enel, when they like to claim they're green, and there it would be trivially easy if there is a resource there for them to plug into their hydroelectric development. So that's that's an example of, I think, a great opportunity. There used to be the argument that, well, you know, geothermal is not convenient because it should be close to a city or something because of transmission losses. Well, that's not really true either anymore, especially with high voltage direct current lines. The Chinese have their country laced with these things. They're sending electric power almost all the way across China, which is like sending it across the United States. So I don't think that objection applies anymore. You got to get, the point is to get the hottest, biggest thing you can, not be next to Santiago or something.
Okay, great. Well, thanks very much for that, John. I'll return to another question of Francisco in a moment. I think there's another question by Maria Fernanda Gonzalez, which I think is perhaps follows on from this point, interestingly. So she asks, how do you think the drilling conditions would be different in a convergent margin setting, like we have here in Chile, not an extensional regime like in Iceland? How might the compressive stresses play a role or complicate matters? Do you have any thoughts on that?
Good question. Everybody says good question to give them time to think. And flatter the questioner. Well, of course we don't know, but I first of all, I would argue that most volcanic arcs, and I actually kind of hate that word because they're not all arcs, and but supra-volcanic subduction, supra-subduction zone volcanism. I think in the vicinity of where magmas are rising, you actually get extension. You're in a locally extensional regime. So I think it's probably not that different stress-wise from the Icelandic situation. There is a difference, and that is that the magmas are wetter. The Krafla magma is only 2.8% water, whereas most people guess 4 to 6% water for silicic subduction zone magmas. And you can't have that at 2,000 meters depth, or more likely 4,000 meters depth. So you have to go deeper for it. The reward is that you get more, besides latent heat of crystallization, enthalpy of magmatic water is a big number also. So you'll have more of that if you have more water in the magma. And that vapor has to come out as the magma crystallizes. So yeah, it's going to take a while to figure this out. Iceland just represents the easiest place to start to try looking at magma because it's closest to the surface and depth is money. On the other hand, I mean, you don't need to be looking for magma now. It would be nice to find, but you can get to a conventional hydrothermal system on the way down there. And, that's worthwhile too.
Okay, many thanks for the answer, Jay. Yeah, I think it's a potentially complicated point. You're right about the water content in rhyolites, but actually in Chai 10, although we had an eruptive obsidian, we found only 1 weight % water in some obsidian that was erupted from Chai 10. So all of these things can.
Well, yeah, but that's because my another heresy I've dabbled in, but I think obsidian is not dry magma. It's magma that's come up as a foam with a lot of water in it and then collapsed, just like a welded tuff. So you got to look at inclusions in phenocryst or something like that.
Of course. A question I had, but I think you sort of already addressed it, is in Chile, where would you drill for magma if you were going to? You talk about Laguna Lomalu, which I agree is a very interesting place. I think another place potentially could be Pajehue Caye, because there we have very good evidence to suggest that there is a laccolith in place at very shallow, a few hundred meters perhaps. I think that would be a really interesting place.
Yeah, that would be fantastic. Near Puyehue. That's that's a fantastic place. I think there are many opportunities. Just at Laguna del Male was my most recent visit, and but I've climbed Puyehue with my kids and marveled at it, at that whole field. The people who've done the most with subduction zone volcanoes are Japanese scientists and engineers, and they have a whole bunch of power plants on kind of andesitic stratocone kind of things. So I think there's a lot to be learned from them. If they'll tell you, they probably will. That's another complication. Wonderful thing about Iceland is that the geothermal company is a hybrid public-private company. They're supposed to make money, but they're supposed to do good. And you never get that in the United States because the companies treat their data as proprietary. But if you're if you're working with a company like Enel or something, and where they stand to benefit, then you can maybe work things out.
John, the director of CEGA, Diego Morata, has a couple of questions regarding supercritical fluids, and so he asks, do you think that supercritical fluid geothermal could be a reality in the near future? And if supercritical fluid geothermal power is enhanced, he thinks it really could become much more interesting in economic terms. But he asks, what do you think is missing to make it a reality?
Well, what's missing is handling the problems that come with high temperature, and it's basically an engineering problem, and both chemical and mechanical engineering problem. One, of course, is the expansion and contraction of the casing as temperature changes. IDDP1 was destroyed by killing it with cold water because the valves didn't work anymore. The wellhead got up to 450 Celsius. and and the valves broke. So then they poured cold water down, and you can imagine taking 2,000 feet of 2,000 meters of casing from 500 degrees Celsius to 0 degrees Celsius in a matter of minutes. But the Icelanders have designed a slip joint for the casing that can accommodate that expansion and contraction. There's been a lot of work on high temperature cement. There are the issues of precipitation of silica and corrosion at high temperatures, hydrogen embrittlement and stuff like that. So, well, we're faced with the problem in drilling a scientific well. We want one that will last. So we're going to put a couple years and multiple millions into trying to develop the right materials to use for supercritical, or I like to say, I've just been reading the history of the term supercritical. There are basically three positions on this. One is you must be above the critical point of both the pressure, for both pressure and temperature of water. One is that you only need to be above the temperature. And another is that it's a bullshit term. It doesn't apply to planet Earth. The argument there is that, you know, it's only a point in a single component system, water. Well, there are no single component systems on planet Earth. There's always something in the water. So, and that changes the critical point dramatically. So it's kind of a moving target. And so recent discussions and modeling of Krafla, people have, and I think the IDDP group kind of overemphasized the getting above pressure and temperature. There were some economic reasons for that, like other people didn't want to get stuck with a drilling bill. And so, anyway, the most recent papers on Krafla call it supercritical. What was I going to say? I think what is really wanted is kind of irrelevant to the term supercritical itself. It's high specific enthalpy. It's just energy per kilogram. And you get that with temperature, not so much with pressure. So, and to be in the single fluid field, not in the liquid plus vapor field. So I'm using the term high specific enthalpy. And you can get that at 2 kilometers or 4 kilometers or wherever. You just want the temperature, really. And to get the temperature, you need to get close to a magma body. You got to get below that conductive zone.
Okay, great. Thanks, John. I think then we're going to leave the last question to Francisco, because he also asked the first question, and it's a general question. He says that in Peru especially, and in Chile here as well, we have a lot of emerging interest in geothermal energy among young students and young scientists.
Good.
And he's asking how to educate geoscientists for the future in geothermal energy. What tools do students need to study or work in geothermal energy?
Wow. Well, I wish someone had asked that before I went to university, because I'm kind of teaching myself as I go along. First of all, I think you can't possibly educate yourself to encompass everything that's needed: the chemical engineering, the mechanical engineering, the petrology, the fluid geochemistry, the electronics of logging. You know, it's huge. What you need to do is have a specialty and then be at least conversant in the other areas so you can talk to people and understand. It's just decide what kind of aspect appeals to the student, whether it's engineering approach or a science, which would be geology and geochemistry, or geophysics, which would be seismology and electromagnetic methods, that kind of thing. And in taking the kind of geology, petrology route, one should have enough mathematics to understand the basics of heat and mass transfer. And also, there's nothing like being on a drill rig, not as a roughneck, muscling things around, but just understanding what happens and what kinds of problems arise. Iceland has a course, a summer course, which of course it won't be your summer, but they have a summer course which is particularly focused on non-European and US. It's particularly focused on non-wealthy countries. A lot of people from Latin America go there. So, and I imagine it's probably well supported. So it probably doesn't, it may not cost anything for the student. I would Google, I'll look this up myself, but I believe it's the Icelandic Geological Survey, which is, well, the acronym is for the Icelandic word, which I don't know, but it's ISOR. And ISOR dot, and everything in Iceland is .is for island. Iceland actually means island, it doesn't mean ice. And they work also with University of Iceland people. And there's another university in Reykjavik, which is more of a engineering-oriented place, and that's Reykjavik University. And they are very open. They have lots of international students. So the short course in Iceland and maybe a year in Iceland would be a fantastic introduction for a student.
Brilliant. Thanks so much, John. Well, I think we're gonna wrap it up there. So thank you a million times for your time. That was fascinating, and there's been lots of comments, and you've generated lots of discussion in our geothermal group here in Chile. So thank you very much for that.
Oh, you're welcome. It's a pleasure.
Great. Y muchas gracias a todos para sus preguntas y sus comentarios. So we'll log off now, and thanks again, John.
Okay,
Speak
thank
soon.
you.